This is our second calculus video, and we're going to be speaking briefly about average gradient again and how it leads to finding derivatives and how we're going to find a derivative using first principles. So you'll recall this diagram from the previous video, and hopefully you recall that if we wanted to find the average gradient of the curve between these 2 points, we would find the difference in the y values and divide that by the difference in the x values. So that's what we did in the previous video. And then we also talked about what would happen, or how much more accurate the gradient of the tangent would be if these points got closer and closer to each other. So instead of Q being here, maybe what if it was there? And then maybe you could get even closer and get it there, or go even closer and get it there. So what I want you to consider is, if this, let's give real numbers because it might actually help. Let's say x was 2. So if we went up 3 places, this would have been 2 plus 3. The h would be represented by 3. But what if we're getting closer and closer and closer? Can you see it's not 3 anymore, and now it's maybe 2, and then it's maybe 1. So we have to think about what's going to happen as h gets smaller and smaller and smaller and smaller, so it is just about on top of p. So in other words, what would happen if h tended to 0? You might remember that from when we were talking about limits in the previous video. So instead of talking about average gradient now, because we're talking about that point getting closer and closer, if it was on top of p, then we would actually be at a tangent to the point P. So the closer and closer and closer that the Q point gets to the P point, and basically think about it landing on top of it, it's actually going to create a tangent. So when you are finding the gradient between any 2 points, now when you're looking for the gradient, you're actually going to find the gradient of this tangent. It's a very important thing to remember right throughout the time that you're doing calculus, that when we find derivative, that word we were looking at the beginning on the first slide, the derivative is the gradient of a tangent at any point. I'm going to keep repeating that. You'll hear me say it quite a lot. But it is an important idea to get across, and you need to keep thinking about it. But it'll all start making more sense as we've done a few discussed a few more things. So let's consider that word derivative. So derivatives can be represented in more than one way. If your function is in this format, f of x equals something, then this is how we will show that we are looking for the derivative, or speaking about the derivative. And you can say f dash x or f prime x. If you look at the explanation on the other side, basically this is what is used to refer to the derivative, which remember I mentioned to you was the gradient, of a function which has been written in this format. So that's the first one. Then if the function is written in the form y equals, then we have to show the derivative using this. Basically we are saying the derivative of y in terms of x. So this is used to refer to the derivative of a function if the function has been written in this format. Then you could also be asked to find derivative, and they don't give it to you in the function format first. They will use what you see here and write a function next to it and ask you to find the derivative in terms of x. Again, this might not be something that makes that much sense until you've actually completed the work, although I'm sure you're watching this for revision, not for learning from the beginning, so these should look familiar to you already then. So in the previous video we came up with this formula for gradient. We did use g of x and and then it was g of x plus h as well, obviously then, but whether it's f of x or g of x or h of x doesn't matter. But we did come up with this. You may recall that originally at the bottom it was an x plus h, because that I should have just left that h. It was x plus h, subtract the x, and then x take away x was nothing, so therefore that's why we ended up with h at the bottom. But this does represent the difference in the y values divided by the difference in the x values. It's just that we happen to have something that cancelled out. However, because remember when I was showing you this diagram, we were talking about what happens if this point keeps on getting closer and closer and closer to a. In other words, h keeps getting smaller and smaller and smaller, and we talked about h tending to 0. So this formula needs to change a little. We want to say we're looking for the gradient if we're speaking about a limit when h tends to 0, and then we can have the formula f of x plus h minus f of x divided by h. So we're going to be using that formula now to find the derivative of a function. So this formula is used to find the derivative of a function, and in particular, this formula is finding the derivative from first principles. So let's have a look at some examples on finding the derivative of a function from first principles. And you can be guaranteed that there will always be a question about first principles. Sorry, I'll change the slide too quickly there. So this is the example we're going to do. We're looking for the derivative of the function x, f dash x, from first principles if f of x is equal to 3x squared. So that is our function. We are trying to find the derivative of that function. So we are going to be using the formula, and remember this is on the formula sheet. The limit as h tends to 0 of f of x plus h, subtract f of x, that's our difference in our y values, divided by h, which was the simplified version of the difference in our x values. So first of all, instead of substituting when you're busy with this formula, which is already quite busy, I would recommend immediately finding f of x plus h and simplifying it so you don't have to do it inside the formula. So if f of x is equal to 3x squared, and you have now been asked f of x plus h, that means any x that we see, we will now write as x plus h. So all we've done is replace the x in the function with x plus h. Let's multiply that out. So x plus h multiplied by itself. FOIL, first and first gives us x squared. Outer gives us plus xh, inner plus xh, so collect them together and it's 2xh, and then the last h squared. Now multiply the 3 in, and now we have our simplified version of f of x plus h. So now we can go back to this formula and write the limit as h tends to 0, and now we are replacing f of x plus h with that we've just found. Subtract the function itself, so that's the function, 3x squared. If the function had 2 or more terms, you would need a bracket to show that you're subtracting everything, and that's divided by h. Now remember, this is as h tends to 0, and when we did the limits in the previous video, you had to have a look at it, and if there was the variable in the denominator which was tending to 0, we had to somehow do some simplifying and some algebra work to make sure it wasn't in the denominator, because we can't go replacing h with 0 when it's in the denominator, because that will make it undefined. So let's work at the top then a little bit. Because we're not replacing, we can't stop writing this yet. The limit as h tends to 0. Notice that 3x squared subtract 3x squared is 0. So we're left with 6xh plus 3h squared, still divided by h. I'm just going to go this way and then I'll clear and make some more room. So note that at the top we can factorize, we can take out an h. So still the limit as h tends to 0, I'm factorizing at the top. There is a higher common factor than h itself. You could obviously take out more than just h. But the whole reason we want to take out h is so that we can do this and say h goes into itself once there as well. So if you took out more, it wouldn't matter, you would still get the same answer. So now we're looking for the limit as h tends to 0 of the function 6x plus 3h. I'm just going to clear that so we can get some space. And now finally we can substitute h with 0, and that is when we now can drop the limit, because we're actually showing what the limit is, substituting. And 6x plus 0 is 6x. I'm going to do a second example before I come back and talk about the answers and what they mean and what we've actually found. But at the moment, accept for the time being that the derivative of the function x is 6x. Okay, so this is our second example. So we're still looking for the derivative of the function x from first principles if f of x is equal to x squared minus 5. As I mentioned before, always find f of x plus h before you really get started. So wherever I see an x in the function, wherever I see an x in the function, I'm now going to be writing x plus h. And then there's still the minus 5 at the back. Multiply this out, x plus h squared, FOIL, so you're basically just using the distributive law, and then collect any like terms if you can, and in this case there are not any. So now we're going to go write down the formula, which is on the formula sheet, so copy it down carefully. Would be a good idea if you knew it, but if you're copying it, make sure you copy carefully. And into this, the limit as h tends to 0. Here's our f of x plus h. Subtract f of x. I'm just going to remove our f of x plus h now. And you may remember in the last example I said to you, if you're subtracting more than one term, because f of x is more than one term, you should use brackets to remind you you're subtracting everything. So let's have a look what we can do on top. So the first terms didn't have any common factors, any like terms. I'm multiplying the negative into the bracket, negative times x squared, and a negative times a negative makes a plus 5. And now if you look for like terms, we have x squared, subtract x squared, and we also have minus 5 plus 5. So they're equal to 0. So we have 2xh plus h squared left over. We need to get rid of the h at the bottom because that's what the limit is. The h is tending to 0. So we will factorize and take the h out in the numerator. H goes into itself once, into there once. So, sorry, I did something terrible there that I always tell everybody else not to forget to do. I think it was because I wasn't working underneath again. This should still say the limit as h tends to 0. And so we're looking for, so the derivative is equal to the limit as h tends to 0 of 2x plus h. Now I can finally replace the h with 0, so I don't need to write the limit anymore. So 2x plus 0 is equal to 2x. So I am going to be spending some time now explaining what we have actually found. So remember the first one we found 6x, and this one we found 2x. So we're going to use a diagram to explain what it is that we've found. So first of all, this function that has been drawn here is f of x equals 3x squared. And then on the right hand side we have the function x squared minus 5. Those two functions that we've just worked with. And we found that the derivative of the first function was 6x, and we found that the derivative of the second one was 2x. So what I need to explain here, and that's why I want to use the visuals to explain it, is you may recall that I was saying that when you find the derivative, you are finding the gradient of a tangent at any point. Let's actually write that here. So if you find derivative, you are finding the gradient of a tangent at any point. The any point is important. So notice that this doesn't really look like a gradient. It looks like a formula. It has a variable in it. So 6x is representing the gradient at any point. So if I chose to make a point where x is equal to 2 and draw in a tangent at that point, then this formula, the derivative here, will give me the gradient if I just substitute 2 in, because I've chosen to draw the point where x equals 2. So the gradient of that tangent is 12. I could also choose to draw at the point where x is negative 1. So there's my tangent where x is negative 1. What is the gradient of that line? I would have to use the derivative, substitute negative 1, and therefore the gradient of that tangent that I've just drawn is negative 6. So when you find the derivative, you are finding the gradient of the tangent at any point. Let's have a look on this side at the other function and do a similar thing. Perhaps I'll choose the point 1, where x is 1, is this point here. If I draw in a tangent there, I can find its gradient by using the derivative. So using the derivative, I'm substituting 1, multiply, and the gradient of this line is 2. I could also perhaps use negative 3, draw in a tangent. Obviously you would normally draw it with a straight line. Substitute negative 3 into the derivative, so the gradient of that line is negative 6. So I hope this visual idea has helped you understand what we were really finding when we used that formula, the first principles, to find us the derivative of the function. We were finding an expression which represented the gradient of a tangent at any point. If we knew the point we were interested in, which we tried out here with 4 different ones, we would then be able to work out the gradient of that tangent. So it's quite long and complicated to use first principles. However, I'm going to now talk about an easier way that we can find the derivative of a function by using rules of differentiation. And what I've written here is representing that, which I'll explain shortly. But it's important to keep in mind that if the question says find the derivative from first principles, you have no choice but to do that. You will not be able to use the shorter way that we're going to look at now. So what I've written here is the general rule. I'm just going to write down the function we found before. We worked with the function 3x squared, and we worked out that the derivative was 6x. We also worked with the function x squared minus 5, and we found that the derivative was 2x. So now I'm going to explain this rule, and then you can look at those to confirm that you understand it. This is saying you take the exponent of the main variable that you're looking at and you put it to the front. So you're basically multiplying it, and you don't just put it to the front. You would also have to times it with whatever coefficient was already there. In this case there's a 1, so n times 1 is clearly still n. So the n times the 1 gives the n, and the new exponent has to be 1 less than the original exponent. So let's use that idea for these two. The 2 multiplied by the 3 gives us 6, and 2 subtract 1 is 1, and you don't really have to write x to the power of 1. You know that that means an x. So hence we didn't write an exponent there, but that would have been 1 less than 2. Similarly, so here we've got a 2, and remember there's an invisible 1 there. So 2 times 1 is 2, and 1 less than 2 is 1. So there's an exponent of 1 there. We're now going to practice a couple of these. So the first one, f of x is equal to x cubed plus x squared. So the derivative, and let's just fill in all the numbers that we can't see. Remember, there is a 1 in front of both of those terms. So 3 multiplied by 1 to put in front, and then 1 less than the exponent. So the exponent was 3, so now it's a 2. And the next one, 2 multiplied by 1 to put in front. And write down the x. 1 less than 2 is 1, so we could write that, but there's no need to really. So there is the derivative. And remember what we found. If we drew this function, this is the expression that would find us the gradient of the tangent at any point. If we were interested in the gradient of the tangent when x is 3, then we would substitute 3 into x's place and find the gradient of the tangent. Let's do another example. Notice it doesn't always have to be f of x, although it is the most common. So if we are looking for the derivative, exponent multiplied by coefficient, 8, 4 times 2. Then x to the power of 1 less than the exponent that we already have. Again, exponent times by coefficient, x to the power of 1 less than the exponent we already have, but we don't bother writing the 1. Again, that is an expression that represents the gradient of the tangent at any point on the function g of x. Let's do one final straightforward one, because as with anything, there's always something a little bit more interesting and difficult to do. Now notice that this isn't f of x equals, it's y equals. And you may recall from the table, or you can look at it in the notes, that when we find the derivative of a function that is in the terms of with y equals, we say the derivative of y in terms of x, dy over dx. Same rule though, multiply the exponent with the coefficient. So negative 4, x to the power of, and 1 less than 2 is 1. And then we have a 1 there that we don't usually bother writing. 1 multiplied by 2 is 2. And now I'm going to put it down. 1 less than 1 is 0, but we'll have a look at that in a second. And keep in mind that if we have a constant, there must have been an x to the 0 there, which we also didn't bother writing. So 0 times 1 is 0. So whatever I wrote here would still be 0, because anything multiplied by 0 is 0. So let's write this in simpler form. So the minus 4x stays the same. And this would be plus 2, because x to the power of 0 is equal to 1. And 2 times 1 is equal to 2. So those are 3 fairly straightforward ones. But now we're going to have a talk about things you have to look for when you're needing to use this rule. There's certain things that have to happen before you can apply this rule that we've just been doing. So here are the 3 points of what could be a problem before you could work out the rule. If there are brackets in a function, you need to remove them. In other words, you need to multiply out, collect like terms and so on before you can apply the rule. So no brackets in a function, we need to get rid of them. If there are any surds in the function, you need to use the surd rules and change them back to exponential form. So if you see any surd, square root, cube root, fifth root, you will need to perform the rule on it that changes it back to an exponent. If you see any variables in the denominator, so if you've got a fraction with something on top and there's an x in the denominator or a y or whatever, we can't use the rule if there's a variable in the denominator. So again, you need to know your exponential rules in order to make sure that variable can be moved to the numerator position. So all of these are going to come up now in the examples I do from here on in. So the first one doesn't have that problem. I did want to do again a fairly straightforward one with you. So determine the derivative of the function f of x. So the derivative would be exponent multiplied by coefficient, so that's 2 multiplied by 2, and the exponent should drop down by 1. 2 take away 1 is 1, so we don't need to write that here. Then we have 4 multiplied by a half, that's 2, exponent multiplied by coefficient. Drop the exponent by 1, 1 less than 4 is 3. And remember that any constant will be 0, because there could be an extra 0 there, and you would get a 0. But let's just stop a second and see why it would be 0. Essentially, you're looking at each one of these terms as a function on its own. You're not looking at it as one big function. Every time you perform the rule, where you're multiplying the exponent by the coefficient and dropping the exponent by 1, you're looking at each term as its own function. So let's consider what the function y equals minus 3 looks like. So if that's going through minus 3, this is the line y equals minus 3. And consider what the gradient of that line is. If we have a horizontal line, the gradient is 0. So this 0 that we are not bothering to write there is representing the gradient at any point of that function, because no matter where I'm looking all the way along this line, the gradient will be 0. Right, the next example, and hopefully you've noticed that one of those 3 points has turned up here. We have a variable in the denominator. So before we can find the derivative, we have to work on the function. So notice this is still g of x is equal to. I am getting the function ready to use the rule to find the derivative. There's nothing wrong with the term number 1, so that will stay as it is. So you have to remember this rule. If you want to move the variables back up to the top, the sign of the exponent changes. I think the rule in this format is the one that's more familiar to you, but you also need to be able to move from the bottom to the top, and you're just changing the sign of the exponent. So I already have a 2x at the top, and now I'm moving the x to the top, and my exponent must change to negative 3. So I'm going to go another step to simplify this further and bring the x's together. X multiplied by x to the negative 3. Remember there's a 1 there, and when we multiply powers of the same base, we add the exponents. And 1 subtract 3 is negative 2. Now it's ready to use the rule. There are no variables in the denominator, and there were never any brackets and so on anyway, but the variable in the denominator was our problem. So now I'm saying exponent multiplied by coefficient, and drop the exponent by 1. Exponent multiplied by coefficient, so this will be plus 4. And be very careful here. Remember, you are subtracting 1. It's negative 2 subtract 1, so we've got a negative 3 there. And it is good practice to not leave your answers with any negative exponents. So I use the rule again to take the x back to the bottom and change the negative exponent to a positive. Right, in this example, you'll see a root sign, and remember I said we don't want any root signs, so just a reminder what the rule of that is. If you were looking for the nth root of a to the power of m, here's your base. The m is basically becomes the numerator, and whatever the root was becomes your denominator. So if you have the square root of y, we can't see an exponent and a number there, but a square root means it's a 2 here, and if there's no exponent it's a 1. So therefore the root of a square root of y would be y to the power of a half. So we're going to need to use that on this one. Again, the function is not ready yet to use the rule and find the derivative, so I'll still call it f of x because I'm just dealing with the function to change how it looks so that I can use the rule. There's nothing wrong with the first term, and then we have the square root of x, which is x to the power of a half. Now I can use the rule. Exponent multiplied by coefficient, 2 multiplied by negative 3, drop the exponent by 1. Exponent multiplied by coefficient, a half multiplied by 5 is 5 over 2. and x to the power of a half subtract 1 is negative a half. I prefer then to carry on and move with the x to the bottom so that I can have a positive exponent of a half. That was a 1 there. Okay, let's look at the next one. Notice now there's brackets and there's also a variable in the denominator. So we don't just have one problem to deal with here, we have two. So let's first multiply out. When one part or one term in a bracket is a fraction and the other isn't, I prefer to make everything look like a fraction so it's clear where the numerators and where the denominators are. So if I times first with first, I've got x multiplied by x, so x squared. The outer 2, I'm multiplying this. The inner 2, and then the last. If you feel you're not very good with fractions, I think it's a good idea to write it on the side. Notice that the outer 2, my x goes into itself once, so my answer is negative 3. My inner 2, x's cancel as well, so it's negative 3. And my last ones, a negative and a negative is a positive. When you multiply fractions, you multiply numerator with numerator and denominator with denominator. We have some like terms that we can collect. And you'll note that it is still not ready to use the rule to find the derivative. So we need to continue going and sort that third term out, which has a variable in the denominator. So we're going to bring the x up and change the sign. So all of this was still the function. Be careful not to show it right there, the derivative, the f dash x. Now we're going to find the derivative. Exponent multiplied by coefficient, so 2 multiplied by 1, and drop the exponent by 1. Note the constant in the middle. Remember what the gradient of a constant function is? The y equals negative 6, it would be 0, so there's no term going there. So now I'm focusing on the third term. Negative 2 multiplied by positive 9 is negative 18. Drop the exponent by 1. Continue in order to show that the x can move to the bottom to give us a positive exponent. And again, remember what we found. This expression represents the gradient at any point on this function. Right, we have one final example to do. You may recall that d of x in the dx, in the table. That's the third way that we can write a derivative. So this is just saying find the derivative in terms of x of this function. Notice the variable at the bottom, but notice it also isn't a nice simple one when it looked like this, for example. There's one term here. There's only one term in the numerator, one term in the denominator, so it is no problem to just move it up and change the exponent. When you have two terms at the bottom, we can't just take the x up, for example. So that usually implies that there needs to be some factorizing, because we would like to try and remove the x minus 1 so that there are no variables in the denominator. So because I'm not using the rule yet, because I'm still trying to work with the function to get it ready to start using the rule, I still need to write dx here. So at the top, you need to notice that we have a difference of 2 cubes. So we can factorize that into 2 brackets. And at the bottom, we have x minus 1. So to factorize this difference of 2 cubes, cube root the first term, keep the sign, and cube root the second term. To find the 3 terms in this bracket, you take the first term of the first bracket we've just had and you square it. To find the last term, you take the second term that you just had and square it. To find the middle term, we multiply these 2 terms together, but change the sign. Notice now we can say x minus 1 goes into itself once and into there once. So now we're finding the derivative of x squared plus x plus 1. Is it ready to find the rule? Yes, it is. There are no variables in the denominator. Although I've got a bracket around it, now I know I mentioned you can't have brackets, there is nothing outside to multiply it with, so the bracket is not really essential. So I can move straight on to the rule, and therefore I don't have to write dx anymore now that I'm busy finding the rule. So 2 multiplied by 1 is 2, drop the exponent by 1. Remember, your x is the same as 1x to the power of 1, so 1 times 1 is 1. Drop the exponent by 1, it's x to the 0, so therefore there isn't a variable in that term. And the last term is a constant, so that must be a 0 as well. So we have found our derivative. The derivative of that function is 2x plus 1. But in the next video, we're going to be finding equations of the tangents to the curve. Remember, we've been talking about the fact that derivative is all linked to tangents. We're now going to, well, in the next video, we're going to find equations of those tangents.